Live coding is an art form in which a performer writes code that synthesizes musical output in real time. Unlike traditional musical performances where musicians control note-by-note output, live coders control the music at a higher level of abstraction by programming and modifying generative algorithms. In these types of performances, it is common for the source code to be displayed as a visual behind the performers, offering transparency into how the music was created. In the live coding language supercollider, a pattern can be as simple as a repeated static phrase. We can make it more interesting by randomizing the pattern. Patterns can also be used to control duration. We can also define patterns within patterns. Expressing patterns manually can be time-consuming, and the output of pattern generators are typically not very melodic. But what if we could use AI to generate melodies for our live coding performance instead? Sequence models have demonstrated impressive results in symbolic music generation tasks, but a few shortcomings prevent them from being viable in a live performance context. One shortcoming is a lack of musical structure in the generated output. Consider this output from a Transformer XL model trained on the DadaGP dataset. While the music makes sense locally, the overall excerpt jumps between three different music ideas without transitions and ends abruptly. To address these issues of structure and controllability, we introduce ReReGP, a Transformer XL model that is able to generate loopable musical phrases of a specified duration and time signature as a tool for live coding performances. ReReGP is trained on the DadaGP dataset, which contains over 26,000 songs and covers genres such as rock, metal, jazz, classical, and EDM. The dataset also includes tokens for expressive performance techniques such as tremolo, palm muting, slides, and string bends, giving it an advantage over MIDI. The song diversity and token expressivity of the DadaGP dataset make it an ideal candidate for live coding performances. As live coding performances often focus on weaving looped patterns together, the main idea behind ReReGP is to address the issue of musical structure by training the model to generate phrases that loop seamlessly when repeated. To steer ReReGP towards generating loopable outputs, we designed a loop extraction algorithm and applied it to the DadaGP dataset, creating a new dataset of loopable phrases. But what makes a musical phrase loopable? We define a loop as a short phrase surrounded by repeated bookends. Using this definition, we can automate loop extraction using a correlation matrix to track repeated phrases within a song. After loop extraction is applied to a song, we surround each loop with repeat tokens and concatenate them into a new file for the loop dataset. We experimented with various training configurations for ReReGP, but found the best results training from scratch on the loop dataset with 15% dropout. We used the same pop music Transformer XL architecture presented in the original DadaGP paper and a cross-entropy loss function. RereGP is designed to allow for configurable duration and time signature during inference. We then post-process the generated output with the same loop extraction algorithm used during training. We evaluated the loop generation capabilities of RereGP compared to a baseline model trained on the original DadaGP dataset. RereGP was able to generate more than 3 times as many loops compared to the baseline. We also evaluated the note density of loops extracted from both models and found that RereGP loops have higher note density per bar across instrument tracks. Here are some interesting loop outputs created by the RereGP model. To evaluate the subjective quality of loops generated by RereGP, we conducted an online listening test. Participants listened to 50 excerpts, each containing a 4-bar loop that repeated 4 times. 25 of the loops were human-made, selected by randomly sampling from the DadaGP dataset. The other 25 loops were machine-generated by the RereGP model, selected without any curation. For each excerpt, participants rated the loop in terms of originality, preference, musical coherence, and loop smoothness. They were also asked to briefly explain their ratings and to predict if the loop had been generated by a human or a machine. We used a linear mixed effects model to evaluate if generation type is a predictor of subjective ratings with participant ID as a random effect. As shown in Table 4, generation type had a significant effect on ratings, and variance of ratings between participants was high. Though our mixed effects model found generation type to be a significant predictor of ratings, the median difference in ratings between human and machine-made loops is less than 1 tick for all questions. It is also encouraging that median ratings of RereGP excerpts were positive for 3 out of 4 questions and neutral on preference. We evaluated participants' ability to discern between human and machine-made loops using a logistic regression model. While the ground truth generation type was found to have a significant effect on perceived generation type, the confusion matrix shows performance was only slightly above chance. These results suggest that RereGP is able to mimic the loopability of the training data somewhat successfully. To identify areas of improvement for RereGP, we visualized the rating explanation free responses as word clouds for each generation type. Simple, boring, and repetitive were adjectives used to describe machine-made loops more frequently than human-made ones, suggesting that future work could focus on increasing the musical variation in generated loops. Investigating the excess repetitions in RereGP outputs, we found that our loop extraction algorithm allows for subloops, where a loop can be made up of smaller loops. Filtering out subloops from the training dataset may help address the repetition issue and could be an area of future work. In conclusion, RereGP was successful at steering music generation towards loopable phrases, resulting in 3 times as many loops as the baseline. Subjective ratings showed a positive response to RereGP overall, but also identified some key areas for improvement in reducing repetitiveness. Compared to the baseline DadaGP model, the addition of duration control and enforcing of loopable generation make RereGP much more viable for use in a live performance context. For future work, we hope to integrate RereGP into SuperCollider as a pattern generator so it can be used in a live coding performance. Thank you for watching.